class 16. I just gave back quiz 3 and project 2. Still working through the stack of homeworks, but I think I'll have them done later today. So if you want to stop by and get them, I'll have them. Otherwise, I'll bring them to class Monday. Project 4 is assigned today, and project 3 is due today. So you want to hand in project 3 before you go, and then check Moodle for project 4. Okay, so we're going to continue our discussion of the chain rule today. So remember, the chain rule is a method for finding the derivative of a composition of functions. We have sort of a mixed notation version, the f prime version. If you want to take d dx of a composition f of g of x, you take f prime of g of x, you take the derivative of the outside function, evaluated at the inside function, so that g stays the same. Then you have to multiply by g prime. Okay, so that is, if you think of it with the stuff version, if you want to take d dx of f of some stuff, you take f prime of that stuff, then times the derivative of the stuff. So we're going to develop a few handy shortcuts for some special uses of the chain rule. What is happening? There we go. So if I want to take d dx of x to a number, how do I do that? Just a plain old like x to the 5th. What would the derivative be? 5x to the 4th, right? So we take the number, bring it down in front, and then we have to the number minus 1, right? So the equivalent rule, but with the chain rule applied, is if I, instead of x, I want to take the derivative of some stuff to a number. So I apply the chain rule, I bring the number down in front, times my stuff, to the number minus 1. But then you have to multiply by the derivative of the stuff. All right, how about e to the x? What's d dx of e to the x? Just e to the x. And then if I want to expand being able to take the derivative of e to some stuff instead of just a plain old x, d dx of e to the stuff is going to be e to the stuff times stuff prime times the derivative of the stuff. Okay, what's the derivative of a to the x? Yep, a to the x times the ln of a. But I want to expand this so that instead of taking derivatives of just a to the x, I want to be able to take the derivative of a to some stuff. So I apply the regular derivative rule. It's going to be a to the stuff times the ln of a, then times the derivative of the stuff. All right, anybody remember from last class what the derivative of sine x is? Cosine x? You're still not responsible for knowing that, but we're using it for chain rule practice. The derivative of the sine function is the cosine function. So if I want to take the derivative of the sine of some stuff, I get the cosine of my stuff times stuff prime. So you apply the normal rule as though the stuff were just an x, right? But then you have to multiply by the derivative of the stuff. Okay, so we want to look at the group activity from last class and see if our new shortcuts agree with the answers we got. So 1 through 4 here. Okay, so g of t is the sine of t squared. So if I want to take g prime, my rule says that if I want to take the derivative of the sine of some stuff, I just take the cosine of that stuff times the derivative of the stuff, which would be 2t. So, oh yeah, I went back a day. Yep. So these should just agree with things that you've already done. Okay, h of x, 2 to the x to the 5 times x. So h prime of x is going to be a product, right? H of x is a product, 2 to the x to the 5 times x. So those are two separate functions multiplied together. So I'm going to start with the product rule, which is first, my first function is 2 to the x to the 5th, times the derivative of the second function, which is just 1, because the derivative of x is 1, plus the second x times the derivative of the first. Okay, so now I have to take the derivative of 2 to the x to the 5, which is a composition. So remember, the derivative of 2 to some stuff is just 2 to the stuff times the ln of 2. So this is going to be 2 to the x to the 5 times the ln of 2. Then I have to multiply by the derivative of the stuff, right? And my stuff was x to the 5th. So what's the derivative of that? 5x to the 4th. Yeah, that's fine. I suppose it would be easy to multiply the x times the 5x to the 4th and make it 5x to the 5th. Yeah, we could do that. Yeah, we could factor out a 2 to the x to the 5, but I don't think that's any simpler. Okay, so for number 3, I want to take the derivative of tangent to the 7th x. So first of all, it's important that you know that that notation means tangent of x to the 7th power. Okay, so mathematicians have just sort of adopted this notation because it means you don't have to write parentheses all the time. So f prime, right? I'm using the power rule. This is some stuff to a number. So I apply the power rule first. It's going to be 7 times my stuff to the 6th, but then times the derivative of the stuff, and they told us that the derivative of tangent x is secant squared x. So if we're going to use a consistent notation here, I would write 7 tangent 6x. So I just wrote my tangent, instead of tangent of x quantity to the 6th, tangent 6 to the 6th. All right, and then the last one, we'll take the derivative. We won't bother simplifying. If simplifying is enough to make you cry, you should probably just not simplify it, unless the directions specifically told you to, because there might be some reason that they want you to like use what you got for something else, and it might be important that it be simplified. All right, so this I'm going to rewrite as x squared plus 9 over x plus 3 to the 1/2. So this is some stuff to a number. So I'm going to apply the power rule first. Stuff to a number. So apply the power rule to the stuff, and I have 1/2 times the same stuff to the negative 1/2. Okay, so I just applied the power rule to the stuff. Then I have to multiply by the derivative of the stuff, which I'm actually just going to write times the derivative of x squared plus 9 over x plus 3. Sometimes I just don't like to do too much in one line because you lose track of what you're doing. So I'll just write down, okay, and then I have to take the derivative of that stuff, and I'll do that in the next line. So I still have this 1/2 times my stuff to the negative 1/2. Okay, then times the derivative of x squared plus 9 over x plus 3, and this is a quotient. So I'm going to use the quotient rule. it's going to be denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. And then what's in the big square brackets there, the quotient rule, I'm going to simplify a little bit because it's easy, but then I'll stop. Okay, so this is going to be 2x squared minus an x squared, so I'm going to get an x squared. Then I have a 6x here, no x's over here, so I have a plus 6x. And then I have a minus 9. Yeah, that's good. X squared plus 6x minus 9 doesn't factor, I don't think. Yeah. If it was plus 9, it would factor, or minus 6x, it would factor. But so we'll just leave it like that. And jump back to today's class. All right, so even though we're usually just going to use these shortcuts that we're developing when we're applying the chain rule, it's still really useful to know the formal version of the chain rule that says d dx of f of g of x is f prime of g of x times g of x. So here's two functions, f and g. And I've given you values of f and g and f prime and g prime at x equals 1 and x equals 2. And I'm going to use those values to find the equation of the tangent line to this function h. And h is equal to 4x squared minus f of g of x. So I want the equation of the tangent line to h at x equals 1. So when you're finding the equation of the tangent line, you need two things, slope and a point. Right? So slope comes from the derivative. So y equals, let's actually use point slope form. Y minus y1 equals m times x minus x1. If we're just going to use a point and a slope, we might as well use point slope form. It's easiest. So m, the slope, comes from the derivative, right? So we just need h prime of 1. Because I'm looking for the tangent line to h. The slope of the tangent line is the derivative of the function. And then x1, that's the 1 that I was given. And then what's the y1? How do I get that? Yes, I would plug 1 into the original h of x, and that will give me my y. So h of 1 goes there. All right, so I need h prime of 1 and h of 1, and I'll have the equation of the line. So h of 1 is pretty easy. I can just plug in here. H of 1 would be 4 times 1 squared minus f of g of 1. We're going to use these values that they gave us. You're right, I don't have a formula. I do not have a formula. Well, what's f of g of 1 means take g of 1 and plug it into f, right? Do you know what g of 1 is? What is it? 2. So this says take 2 and plug it into f. Do you know what f of 2 is? Yeah. So we actually do have enough information even though we don't have a formula. We wouldn't be able to do it. Yeah. This problem was specially designed so that I gave you just enough information to be able to do this particular question. So this is 4 minus f of 2, right? So I just replaced g of 1 without it equals, which is 2. And f of 2, they gave me as 7. So I get negative 3 is my h of 1. So that is going to go here for y1. All right, so that's what I've got for y1, and then I just need the slope. I need h prime of 1. And I think I need more room. So 4x squared minus f of g of x. Okay, so h prime of x, the two terms that are separated by subtraction, you can take their derivatives separately. So the derivative of 4x squared is 8x minus, and then the derivative of a composition, we use the chain rule. The formal definition of the chain rule says, well, you take the derivative of the outside function, evaluate it at the inside function, times the derivative of the inside function. And then I need h prime of 1, so I'll plug a 1 in here. 8 times 1 minus f prime of g of 1 times g prime of 1. All right, so let's work on f prime of g of 1. What is g of 1 according to the values they gave us? 2. So I'll just replace g of 1 with a 2. So this says 8 minus f prime of 2 times g prime of 1. And then what's f prime of 2? 10. What's g prime of 1? Negative 6. So this says 8 minus negative 60. 8 plus 60 is 68. So I have my h prime of 1, which is my slope. So my equation, now that I have h prime of 1 is 68, I can write my equation y minus y1 equals m times x minus x1. My slope is 68. My x1 is a 1, that's the x that I was given. And then y1 we figured out earlier was negative 3, so this becomes plus 3. And there's the equation of the tangent line. And if you like y-intercept form, you could use that too. Or you could change this to y-intercept form from here, whatever method you feel comfortable with. All right, so remember, when you're taking the derivative of a composition, take the derivative of the outside function, evaluate it at the inside function, then multiply by the derivative of the inside function. Sure, yeah. All right, so I'm using, this is the same, a continuation of the same problem. I'm still using those 8 values of f and of g and of f prime and of g prime. So I want to take the derivative of f of x to the 4th. And I want to evaluate it when x equals 1. So the derivative of f of x to the 4th, let's just do that first. So that looks like some stuff to the 4th power, right? So I'm going to apply the power rule to the stuff. So I get 4 times f of x cubed. But then I also have to multiply by the derivative of the stuff. So times f prime. And then they want me to take this evaluated when x equals 1. So if I plug in a 1, I get 4 times f of 1 cubed times f prime of 1. So let's see, f of 1 is 4. 4 cubed is 64. And 64 times 4 is 256. 4 cubed is 64, right? Yeah. Okay, and then f times f prime of 1, which I go up to my table of values here, and I say f prime of 1 is negative 2. 256 times negative 2, negative 512. All right, take a few minutes and look at the next one. And think about how it's different from the first one before you start trying to take its derivative. All right, so this one's a little trickier because the outside function isn't a standard rule that we know, right? If you look at the problem we just did, my outside function was some stuff to the 4th power, and I know that's a standard rule. I know how to take a derivative of some stuff to a power, right? So my outside function here was x to the 4th, and my inside function was f. But when I move to this problem, what makes it different is that my inside function is x to the 4th, and my outside function is f. And the chain rule says take the derivative of the outside function first. So my d dx of f of x to the 4th is going to start by taking the derivative of the outside function, the derivative of f, evaluated at the inside function, times the derivative of the inside function. And the derivative of the inside function would be what? 4x cubed. Then I'll evaluate that at 1. So I have f prime of 1 to the 4th times 4 times 1 cubed. So f prime of 1, that's negative 2, times 4 times 1 is negative 8. Any questions? So sometimes you have to apply the chain rule repeatedly in the process of evaluating d dx of some stuff. You might have to use the chain rule again. Okay, so we'll do a couple examples where that happens. All right, so I want to find the derivative of 9 to the 5x to the 7th plus 4x to the 8th times e to the 3x, all raised to the 9th power. Okay, so what's my outer function here? To the 9th. Yeah, I have a bunch of stuff to the 9th. So when I find y prime, that's an arrow. Okay. Y prime is going to be, first apply the chain rule. Get a bunch of stuff to the 9th. So this is 9 times the stuff, 9 to the 5x to the 7th, plus 4x to the 8th, e to the 3x, all raised to the 8th power now. So I applied the power rule to my stuff. But then I still have to multiply by the derivative of the stuff, of the inside function. So I need to multiply by the derivative of 9 to the 5x to the 7th plus 4x to the 8th times e to the 3x. So I have a bunch of stuff to the 9th, apply the power rule, and I get 9 times the stuff all to the 8th, but then times the derivative of the stuff. And I didn't try to take the derivative of the stuff in this step because it's complicated. So I will take that derivative in my next line so that I don't lose track of what I'm doing. Okay, so I still have this first term, my original 9 times the stuff. Oops. Okay, now I want to take the derivative of the stuff. So when I want to take, this is a sum, these two terms that are separated by addition, I can take their derivatives separately. So the derivative of 9 to the 5x to the 7th, that looks like the derivative, that looks like 9 to some stuff, right? The derivative of 9 to some stuff is 9 to the stuff times the ln of 9. So this will be 9 to the 5x to the 7th times the ln of 9. So that's my 9 to the stuff times the ln of 9, but then I still have to multiply by the derivative of the stuff. And the stuff was 5x to the 7th, so the derivative is 35x to the 6th. Okay, so that's the derivative of this term. Now I have to take the derivative of this term, which is a product. So maybe I'll just do that in the next line. Plus the derivative of 4x to the 8th e to the 3x. And it's fine if you want to do these all at once. I just tend to lose track of like, wait, what the heck am I taking the derivative of? Am I taking the derivative of the stuff or the original or the outside function? I can't remember. So I like to stop, you know, and just have it all written out. Okay, so now the next thing I have to take the derivative of is this product. So I'm going to write tiny here. Okay, so now I want to take the derivative of this product, 4x to the 8th times e to the 3x. So I'll treat this as 4x to the 8th is my first, and e to the 3x will be my second. So I have first 4x to the 8th okay, first times the derivative of the second. What's the derivative of e to the 3x? Yeah, e to the 3x times 3, because this is e to some stuff, right? The derivative of e to some stuff is e to that stuff times the derivative of the stuff, which is 3. Okay, so I have first times the derivative of the second plus the second, e to the 3x, times the derivative of the first. What's the derivative of 4x to the 8th? 32x to the 7th. Good. And I'm not even going to try to simplify it. That is fine. Yeah. So I applied the chain rule multiple times, right? I had my outer function, the x to the 9th, and then I had to multiply times the derivative of the inside. And then when I was taking the derivative of the inside, I applied the chain rule when I was taking the derivative of 9 to the 5x to the 7th, and when I took the derivative of e to the 3x within the product rule. So there were 3 chain rules in there. You want to try one? Okay, you try the next one. Okay, so let's do this one. Y prime. So first you should see that as a bunch of stuff raised to the 1/2 power, right? You want to think of that square root as the 1/2 power. So I've got some stuff to the 1/2. So I apply the power rule to the stuff. 1/2 times all this crazy stuff, e to the sine of of 2x minus 4 cubed to the negative 1/2. Right, so that I applied my power rule. So I just had a bunch of stuff to the 1/2. I brought the 1/2 down and made the exponent 1 smaller. But then I have to multiply by the derivative of the inside times d dx of all this stuff. So I need the times the derivative of e to the sine of 2x minus 4 cubed Okay, so I still have this same first factor. Okay, now I have to take the derivative of e to the sine of 2x minus 4 cubed. Well, what's the derivative of e to some stuff? Yes, e to some stuff. So the derivative of e to the sine of 2x minus 4 cubed is e to the sine of 2x minus 4 cubed. But then I have to multiply times the derivative of all this stuff, the derivative of the inside. So now I have to take the derivative of the sine of 2x minus 4 cubed. So I have to apply the chain rule again in the midst, the chain rule within the chain rule. Okay, so write all this stuff down again. Okay, now the derivative of the sine of some stuff is what? Cosine of that stuff. So I've got the cosine of 2x minus 4 cubed. Then you have to multiply by the derivative of the stuff. So the derivative of the sine of some stuff is the cosine of that stuff times the derivative of that stuff. Almost done. There's a lot of copying here. Okay, so now I've just copied everything down, and now I just have to take the derivative of 2x minus 4 cubed. So that is some stuff to a power. That's some stuff cubed. So to take its derivative, apply the power rule. 3 times 2x minus 4 squared. But then you also have to multiply by the derivative of the stuff, which is what? 2. And I could multiply the 3 times the 2 times the 1/2 in the front, but I don't care. There's my derivative, unsimplified. Crazy. So how many chain rules did we do here? 4. Yeah, each time I wrote down a d dx. That was 1, 2, 3, and then I had one last one here, but I just wrote down, I didn't write d dx, I just put the derivative. So 4 chain rules at once. So this is a composition of 4 functions. So I had to apply the chain rule 4 times. So here's what the chain rule looks like using the prime notation for a composition of 4 functions, which is exactly what we just did, right? If you want to take d dx of f of g of h of j of x, first you take f prime evaluated at everything on the inside, g of h of j, then times the derivative of what's inside, g of h of j of x. But to take this derivative, you're going to have to apply the chain rule. So we have this first step, we just rewrite it, times g prime of h of j of x times d dx of the inside h of j of x. And so on and so on. And you stop, you know you're done taking derivatives when your inside function is just a plain old x. Okay, because then you could use the chain rule one more time, right? But your inside, the derivative of your inside function would be 1. So then you'd be done. And this is the Leibniz notation for a composition of 4 functions. If you want dy dx, you do dy dA times dA dB times dB dC times dC dx. Where y is a function of a, and a is a function of b, and b is a function of c, and c is a function of x. Okay. So you notice that the Leibniz notation looks like a chain of linked derivatives, and that's why we call it the chain rule. Okay, some more stuff for you to work on. I've given you some values, kind of like the problems we did a little earlier in class, like number 4 here. Giving you some values, and you are to find some derivatives.